I want to make sure everyone's really super cool with kind of how we're writing these systems of equations, because there's like probably 4 different ways you can write things, which is kind of unfortunate, right? It'd be kind of nice if there was just one way to do it. But there was one, what was that problem someone was asking about? So I want to just make sure you can see so many things on my screen that I want to move around. There was a very specific problem. Where did you go, problem? Yeah, no, okay. That, yeah, it's fine. Yeah, I am not, oh, there it is, I see, okay. So I want to, yeah. So let's look at this system of linear differential equations. I have the following. dx1 dt equal to 2x1 plus 8x2. And I have dx2 dt equal to 6x2, which you might write for your convenience as 0x1 plus 6x2. So we can write this in a few different ways. One way to write this is as a matrix equation. So the dx1, dx dt, and dx2 dt, those become the components of the derivative matrix. So this is dx1 dt, dx2 dt. The coefficients here in order of, right, x1's first, x2 second, so the x1's are first, the x2's are second. The coefficient matrix is just those coefficients. By the way, stop me if you have questions or interject or whatever, write something in the chat. And then the variable vector or matrix is right there. And this is the way I would usually write it. But there are other ways to write it. So people, you can write this, you can write dx dt equal to a times x. And I like to write little arrows, but you could also write it without the arrows. In fact, in problem, what is it? In problem, where'd you go? I literally was just looking at it. Sorry, I had it and I lost it. In problem 11 of your homework, they write something like this. They write dx dt equals, I'm going to just use the same thing here, 2806x. They don't use any arrows or anything, but it's definitely your responsibility to know, oh, well, they obviously have to mean that x is x1, x2. Because you can only multiply a matrix by another matrix that's 2 by something. Because, well, I should say, this 2 by 2 matrix, right? If this is 2 by 2, the dimensions of this have to be 2 by something. 2 by 1 in this case. So they really kind of maybe should have used this notation, but they didn't. So that just means that, and the vector dx dt just means dx1 dt, dx2 dt. So make sure you're okay with that. Make sure you're comfortable writing these equations in any number of ways. But this specific problem, let's go back and look at it. This problem is asking us to do the following. It's asking us to solve the initial value problem. So they're also giving us, in addition to this equation, they're giving us that x1 of 0 is equal to -11, and x2 of 0 is equal to, what have we got here? -4. And again, right, there are lots of ways of writing that too. I've definitely seen, right, you could also write this as x of 0, or x of 0 with a vector is -11, -4. So again, really incumbent upon you to get comfortable with seeing how things are vectors in this system of equations. So back to the problem. The problem says we want to solve this. So, and specifically, they're asking us to solve it, and they're asking us to write what x1 of t is and x2 of t. So notably here, right, when we solve the system of equations, we know what the solution looks like. Ah, man, red pen on the floor. I feel like I should do something about that. I guess I'll do something about it later. Red pen on the floor is never good. And I lost my cap too. Oh, there it is, right there. Okay, sorry. So here's the deal. We know what this looks like already. We know that the solution to this linear system of differential equations, and I'm going to say this a lot, the solution to a linear system of differential equations always looks like this. C1 e to the lambda 1t times the vector v1 plus C2 e to the lambda 2t times the vector v2. If you haven't memorized this already, you want to memorize this. It's gonna keep coming up over and over and over. Okay, so our job is to find the lambdas, the v's, and then eventually the c's. Our matrix was, forgot what it was. Our matrix was this matrix 2, 8, 0, 6. This is one of those nice ones. Everybody in the chat right now, it should take 10 seconds, should be able to tell me what my two eigenvalues are without doing any work. So I would love to see people in the chat write what the eigenvectors are. I'm not even looking at the chat right now. I'm giving everyone a chance to respond. Yeah, exactly. 2 and 6, right? We've got this 0 down here or 0 up there or both. So cool. I'm going to say lambda 1 is 2, lambda 2 is 6. And now we're going to find the associated eigenvectors. Be careful though, right? If you have a matrix like this, 0, 3, 4, 5, you don't get any kind of cool information, right? You don't get to say the eigenvalues are 3 and 4 or 0 and 5, right? I have no idea what they are without doing more work. It's only if there's a 0 there or there. So then for lambda equals 2, we're going to solve the equation, our matrix times the eigenvector, which we're going to find. I think he's partial to writing it as v11, v12, right? So it's the first eigenvector, and then it's the first component, the second component of it. Whatever you like. I use x and y typically. It doesn't really matter. This is going to equal the eigenvalue times the eigenvector. So then our first equation is going to give us, and I'll write it up here, 2 times v11 plus 8 times v12 equals 2 times v11. The 2 v11s cancel out, and 8 v12 equals 0, so v12 has to equal 0. And we know when one of the components is 0, the other one is anything except for 0, and we choose 1. So our eigenvector here is going to be, I'm going to write it right here, v1 is going to be the eigenvector 1, 0. v12 we just found out to be 0, that means v11 gets to be 1. You could pick 6, but why would you? You could pick 7, you could pick pi, but you're going to pick 1. Okay, let's do the other one, lambda 2 equals 6. So now we're doing the same equation, our matrix times our next eigenvector, which I'm going to write the following way, which is best lazy. I'm going to write it as v21, v22, right? Because it's the second eigenvector and it's still the first component and the second component in the second eigenvector. Equals, now instead of 2, we're going to use 6. Oops, I wrote the wrong things. This is why I use x and y typically. But again, I really want to emphasize everything. I want to make sure you understand it doesn't matter what you call these components because you're just solving for them and then getting an actual vector. So using my first equation again, well, no, actually, yeah. Using my first equation, I get 2v21 plus 8v22 equals 6v21. So subtract there, you get 8v22 equals 4v21. I would divide everything by 4. and say 2v22 equals 1v21. So v21 is 2 and v22 is 1. So our v2, I just said the first component, v21 is 2 and v22 is 1. Right? So just as a reminder to everybody, when you're figuring out what's what, you can just set one of them to be a constant. So like you can say, I'm going to let v22 equal 1, and then 2 times 1 equals v21. So, whoops, no, that's right. So v21 has to equal 2. The other way you can think about it is the coefficient of each thing is the value of the other thing. So the coefficient of v22 is 2. So v21 ends up being 2. The coefficient of v21 is 1. So the coefficient of v22 ends up being 1. Right, so that when you plug in 1 here and 2 here, it's equal. Okay, so now we have almost everything. Yeah, so now I have to find, we have almost everything except a place to write anything down. So here's our eigenvectors and eigenvalues. Let me erase all this, but before I erase all this, are there any questions about what we've done here? Okay, well, we're gonna erase. So here is our, let me also write down what our initial conditions were, right? We had that x of 0 was equal to, I forgot, the -11, -4. So then plugging in, or sorry, writing the whole equation, we're going to get the x of t, which is x1 of t, x2 of t, is equal to c1 e to the lambda 1 times t times v1 plus c2 e to the lambda 2 times t times v2. We still have two things left to do. We have to find the constants, and we have to do another thing too. Now, I want to make sure everybody knows this. The constants aren't just -11 and -4. They're never going to be what these are. Or, I mean, I suppose you could probably make it weird so that they came out to be the same, but that would be a huge coincidence. You have to try to make that happen. What we have to do is we have to actually set t equal to 0. And if t equals 0, here's the equation we have. Well, if t equals 0, we get -11 and -4 for x1 and x2. And every time when you set t equal to 0, e to the 0 is going to become 1. So you're going to get c1 times 1, 0 plus c2 times 2, 1. And you can tackle this however you want. My preferred way, especially when there's a 0. So here's what I'm really doing. I'm writing out the two equations. I'm writing out, in fact, I could actually add these together. So I'm really thinking of it as -11, -4 equals the one vector c1 times 1 plus c2 times 2. And then in the second row, c1 times 0 plus c2 times 1. That's what we're doing. So then c2 is equal to -4 because, and it's always going to be easy this way if one of the things somewhere is 0. So c2 is -4. And then if c2 is -4, we get -11 equal to c1 plus 2 times -4 is -8. So add 8 to both sides and c1 equals -3. Okay, so a normal person, okay, fine. This maybe is a little too strong. The way I would prefer to write the final answer to this system of equations is the following way. I would want to write it as the vector x of t, which is just x1 of t, x2 of t, is equal to c1, which is -4 e to the 2t times 1, 0 plus, well, really, let's make it a minus, plus -3 or -3 e to the 6t times 2, 1. However, that's not how they're asking you to write your answer in this problem. The question specifically asks you, what is x1 of t and what is x2 of t? So then you have to remember, oh, okay, this is what x1 of t, x2 of t is equal to. So the top row component is the x1 component, and the second row or the bottom row component is the x2 component. So if I was trying to figure that out, I would say, okay, x1 of t is -4 e to the 2t times 1 minus 3e to the 6t times 2, which I would simplify, right? I would write this as -4 e to the 2t minus 6 e to the 6t. And x2 of t would be -4 e to the 2t times 0 minus 3e to the 6t times 1. So that would be minus 3e to the 6t. So that's how you find the x1 and x2 component. The x1 component is just the things in the top row added together. The x2 component is just the things in the second row added together. Shouldn't -4? Oh, could be. I could have blown it. Shouldn't -4 and -3 be switched? You are correct. Thank you so much. Yeah, right. My C2 was -4. My C1 was -3. Oh, good catch. Thank you so much, Julia. So let's go fix that. This should be a -4. Okay, so this should be -3. This should be -4. So then this should be -4 e to the 2t times 1. Or not. -3 e to the 2t times 1 minus 4 e to the 6t times 2. So you're going to -3 e to the 2t minus 8 e to the 6t. Sorry about that. And then the second row will be still 0 and then minus 4 e to the 6t times 1. So that'll be a -4. Yeah, good eye. Thank you. Questions about this? Whoa. Let me sit in my seat here. So let me actually use this example just to show you guys a couple cool things about p-plane. So let me, I don't want this up right now, but you kind of can't go away. That's fine. Let me share my screen. Yeah. So here's some, so one thing you can do, which I think is kind of cool, is that you can, instead of actually writing the numbers in here every time, you can just say it's ax plus by and cx plus dy, and then you can put a, b, c, and d down here. So for this one, and I've definitely lost my matrix here, my a, b, c, and d are 2, 8, 0, and 6. So I'm going to plug those in. To, whoops, that's not a 2, 2, 8, 0, and 6. And then we can, let's make our window a little bit bigger. Sure. Yeah, right. Okay. And let's graph it. Oh, and so I have something already on there that you guys should see. So those things right there, I believe those are the, well, let's actually take a look. So you have options, which I think is kind of worthwhile. You can display the, where'd you go? Nope, not there, not there. There was something, a solution. You can show the null lines. You can also show the null lines in arrows. But if you show the arrows, it takes away all your other arrows. So just so you know, right. So this is what we were doing last class on Friday, where I was like, okay, so clearly this red line is the dx1 null line. Because if you set dx1 equal to 0, you're saying the x1 change, which is the horizontal change, if you're thinking x1 is x, is 0, meaning all of your change is vertical. So this is definitely setting 2x1 plus 8x2 equal to 0. If we solve for x2, we get 8x2 equal to -2x1. We get x2 equal to -1/4 x1, or y equal to -1/4 x, which is totally what that line is. On the other hand, if you set the second one equal to 0, you're just setting 6x2 equal to 0 or 6y equal to 0, and you're getting the line y equals 0, which is the horizontal line. And that's, so if dy dt or dx2 dt is equal to 0, that means all of your change is not vertical, right? There's no vertical change, it's all horizontal. There's something in the chat. No, so null lines are where, so there's two null lines. Well, so actually I should say there can be multiple null lines when the system of equations, when the system of equations are linear differential equations, you're always going to get exactly two null lines. One where dx dt is equal to 0, and one where dy dt is equal to 0. Or in the notation I've used in this problem, dx1 dt is equal to 0 and dx2 dt is equal to 0. So this null line here, this red one, is where dx1 dt is equal to 0, which gave us the line x2 equals negative 1/4 x1, which is totally this line, right? This line totally has a slope of negative 1/4. And then the second null line, I'm just setting dx2 dt equal to 0, which I'm just setting this equal to 0. You're just getting x2 equal to 0. So I'm totally getting, oh yeah, y equal to 0, x2 equal to 0. I'm getting the horizontal line. What's also cool, yeah, of course. Yeah, Ethan. So for example, when we start, if we look at non-linear differential equations, and let me stop sharing for a second. Let me just show you, like, if your system of equations was something like dx, well, let's use x and y to make it a little easier. If you had to say like dx dt equal to x squared minus x, and dy dt was y minus x squared, then setting this equal to 0 will give you x equal to 0 or x equal to 1. So you have two vertical lines that are null lines. Setting this equal to 0, you'll get y equal to x squared. So you'll have a parabola that's a null line. So you can definitely get null lines that are not just straight lines if you have a system of non-linear differential equations. This thing is so in the way. But the other thing I wanted to show you guys, which I thought was kind of cool. Well, come on, share my screen here. Which is that you can also graph the eigenlines. If you go back to the, whoops. Okay, yeah. So we go back to, let me graph this again, just so it's there. Okay. So the thing is, if you've got the null lines turned on with, keep forgetting where the things are in the solution. If you have the null lines with arrows, you can't see the whole thing. But if you find the equilibrium point linearization, no, that's not one. The stable and unstable orbits. Let's graph the phase plane. Okay, fine. We need to like redo it. There we go. There's the thing. So let's graph it again. Sure. So those are my null lines. And then if you click on the solution thing again and you find the stable and unstable orbits, and you click like anywhere. Oh, did I actually click the wrong? Maybe I picked a system that's not great for that. Okay, fine. Maybe there aren't any stable ones there. Yeah, bummer. Okay. Anyway, sometimes you can see the eigenlines, which is kind of cool. I think it only works if you have a saddle though, which is too bad. Oh, interesting. And then if you click on points, right? So our initial condition was too big for this, -11, -4. So let's make our window a little bit bigger. Let's make our x minimum like -15. So if we go over to -11, -4, we can see that, oh yeah, it's going to go out away. And also, and I'm saying a lot of things, but they're all kind of relevant. Looking at this system of equations, we can see that, right, let me stop sharing here. Actually, yeah, we can just go back to the origin. If you start just clicking right at various points, everything's going to shoot outwards because both of my eigenvalues are positive. And my eigenlines, if we wanted to try and land on them, my eigenlines would just be the line where y equals 0, x1 equals 1. So right, it's just over. Right? So if we go in the purely horizontal direction, right, it's hard to get it right on there, but you get the idea. And then the other eigenline would be this one here, where we're over 2 and up 1. So if we go, over 2 and up 1. That's kind of an eigenline as well. Okay, so p-plane is fun. I really think you guys would be well off using it, especially when we start trying to say things about what kind of solutions we have. That said, and we'll probably do this on Wednesday, I know that this system of equations, once we found the eigenvalues were +2 and +6, I knew that we were going to have arrows pointing outwards from the origin. So it's an unstable node is what we call it, right? So there's no stability anywhere. Once you're a little bit off of the equilibrium point, you're just like everything, you just move further and further and further away. Are there other questions about this before we move on to another example? I should stress that the process for solving a linear system of differential equations is always going to be the same. You're going to find the eigenvalues. Well, at first you're going to write the matrix. Then you're going to find the eigenvalues. Then you're going to find the eigenvectors. Then you're going to write, your solution is C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. And then the last step is to find C1 and C2, and then write your solution as the actual C1 value times e to the lambda 1t times V1 plus the actual C2 value times e to the lambda 2t times V2. It's always the same, like 4 steps. Eigenvalues, eigenvectors, find the constants, write the solution. Okay. So let's see. People had questions about that one as well. Let me grab the. Sorry, I've got, as usual, I have a bajillion things open. So I want to say, I think people problem 9 and 10. Let's look at 10. Oh yeah, 10 looks. So 10 is both very much the same and looks very different. And again, I'm just going with the assumption that my problem 10 looks different enough than your problem 10, that I'm not exactly doing the homework problem for you. That said, if I happen to be exactly doing the problem with your numbers, you should still do the work, right? Just getting the answer on your homework is not going to be super duper helpful as far as learning the material. So yeah, let's look at this one. So problem 10 says, suppose that the matrix A has the following eigenvalues and eigenvectors. Great. So they're giving us lambda 1 is -3 with V1 equal to 1, 1. And lambda 2 is +2 with V2 equal to, now I think it's funny that they've written V2 this way. So they've written V2 as 2, -2. But you could, you could have written anything, right? You could have written 3, -3, 4, -4. It wouldn't have mattered. Most people would normally write 1, -1 for this other eigenvector. That's all right. So I want to write the solution to the linear system. I don't know why they're using R's here, but they've used R's. So I want to find the solution to the linear system R prime equal to A times R. And there's something I want to say about this. Oh, here's what I want to say. Before we do anything, I know this linear system of equations, the solution looks like the phase plane looks like a saddle. So that because one of the eigenvalues is negative and one of the eigenvalues is positive. It's kind of cool, right? We definitely have that. And again, the idea here is that if you were to graph this, I know I'm going in a different direction, but I think it's worth our while. So 1, 1 is one of the eigenlines. Let's graph it in red. And since the eigenvalue associated with it is negative, the direction arrows point inward towards the equilibrium. And then the other eigenline is going to be this one here, where you go over 2 and down -2. So, or over 1, down 1. So it's going to look like this. And it's not always the case, but sometimes it is the case. Well, that one does not look very straight, but sometimes your eigenlines are going to be totally perpendicular. So what this means is if we start like somewhere like here, we're going to get pushed this way and this way. We're closer to this one, so we're going to kind of get pushed this way, but then we're going to like go like that. And if we start, up here, it's going to do something kind of similar. Same kind of deal over here. So wherever we start, unless we start exactly on that eigenline associated to the negative eigenvalue, if we started there, we would get pushed totally towards the origin. But if we start even just a little bit off of it, right, like right there, we get pushed, but then we're getting pushed that way as well. And then the same kind of stuff over here, right? And it definitely looks like a saddle, which is what you're always going to get when you have one negative and one positive eigenvalue. Anything else I want to say about that? Maybe we'll look at the graph of this on p-plane after we're done with it. So let's take a look here. We're trying to write the solution in the following form. So they're giving us the whole kind of deal. They're saying we want to write x of t, y of t equal to c1 blank blank e to the blank times t plus c2. They're writing the vector first, which I feel like is weird. E to the blank t. We know what this is, right? The solution to the system of equations is c1 e to the lambda 1. That's right. So this part here, this is your c1 e to the lambda 1 t times v1. So the blank in front of the t should just be my lambda 1, which is -3. And my v1 should just be this here. And then for over here, my blank in front of the t here should be my lambda 2, which is +2. And my eigenvector is 2, -2. And then they want you to write this in the fundamental matrix form. That's a good question. Okay, so then they want you to write this as something times the matrix. Ooh, that's weird looking. Okay, so it's weird looking, but we can figure it out. So I can totally understand why you guys would ask me this question in your reflections, because like definitely the second way of writing it seems weird. They want you to write now. This is not the most straightforward way of doing it. They want you to write x of t, y of t equal to a matrix, a 2 by 2 matrix, times the vector c1, c2. Okay, so let's write this out. If we write this out as one vector, right? This part is equal to c1 e to the -3t plus c2 times 2 e to the 2t. And the second row, so this is one entry. And the second entry in the second row is c1 e to the -3t minus c2 times 2 e to the 2t. But then we want to write this as something times c1, c2. So in the first row, we need e to the -3t times c1, and we need 2 e to the 2t times c2. In the second entry, we need e to the -3t again times c1, and we need minus 2 e to the 2t times c2. That's a kind of strange way of writing it, but that would also be technically correct, although it feels a little bit atypical to me. Okay, and then the last way, and then there's a third way they want you to do it, which is also silly. Then they want you to say what x of t and y of t are separately. So I'll just point out, this here is your x of t. this here is your y of t. So as you can see from this problem 10 in your homework, there are lots of ways of writing the solutions to a system of linear differential equations. The way I would probably default to is this first way here. That's how, which is actually, no, yeah, that's the part. So this is probably, in my opinion, and I think actually the most standard way of writing your solution to a system of linear differential equations. Questions about this? Notably, we don't actually have the matrix, which is also fine. Let's look at one more. So people did ask me about problem 12 as well. Let's look at problem 12, which I've made it my own matrix for problem 12. I don't feel like, so I don't know how many of you attended lecture today, but I don't feel like he said in lecture really anything new to any of us, right? I think everything he said in lecture today, I've already kind of said in co-class, right? We know how to solve a linear system of differential equations. But let's go ahead and look at this problem 12, which again is kind of weird. So they're giving us the following. They want us to find the derivative of this vector AB times e to the kt, which you could write as the derivative of ae to the kt b. We know how to differentiate e to the kt. It's a times k e to the kt, and it's b times k e to the kt. So writing that in the way they want it, no, I feel like this is what they want, right? So this would be what goes in the first blank. This is what goes in the second blank. If you're wondering what I'm talking about, I'm assuming everyone's looked at problem 12 in homework. If you haven't, you should, so you know what I'm talking about. Okay, so let's go ahead and then do the next part, which is we want to find k so that, let's see, I picked some numbers right here. And in fact, I picked, yeah, so that, trying to make this work out right. Find k so that 1 negative 1 e to the kt is a solution to, and what have I got here? Yeah. Negative 1, negative 3, 5, negative 7, no, 5, 7, yeah, times, sorry, they're writing it in a weird way, so that x prime is equal to this times x. So, again, kind of a weird way of phrasing it. What they're saying here is they want this to be your x. So I want this to be a solution to this equation. Okay, so I'm going to find x prime. But look, we already know the first part of this tells us how to find x prime. How do we find x prime? Well, the derivative of ab e to the kt is ab k e to the kt. So our x prime, right, the derivative is going to be exactly that. It's going to be ab k e to the kt, and it's going to equal 1 negative 3 5 7 times our x, which is 1 negative 1 k e to the kt. Okay, now here's the cool thing you can do here. K is, I believe, supposed to be a not. Could k be 0? I don't think k is supposed to be 0. Yeah, I'm going to go ahead and safely say that k is not 0. Also, e to the something is never 0. So we can divide both sides by this and this. And now we're just left solving. I feel like oh, you know what? I made a tiny error, not a huge deal. there shouldn't be a k over here. Meaning this shouldn't be 1 negative 1 k to the kt. This should be 1 negative 1 e to the kt. Right? That's what our x is. And this should be k e to the kt, which is what our x prime is. So great, now I don't have to worry about canceling the k, which could have been 0. But I can definitely cancel the e to the kt on both sides. So now here's what we're left with. This left side, k negative k, equals the right side. 1 times 1 plus negative 3 times negative 1 is 4, which feels like the wrong number. Oh, I missed a negative 1 there. That's why. Negative 1 times 1 plus negative 3 times negative 1 is negative 1 plus 3, which is 2. And 5 plus negative 7 is negative 2. So it looks like k has to equal 2. And the idea here is that k is actually the eigenvalue. So here's what they've really done without saying the words. They've given you 1 negative 1 as one of the eigenvectors, right? Because they're trying to write the solution as c1 e to the eigenvalue times t times the eigenvector. They gave you the eigenvector and they're saying, okay, use this weird relationship to find the eigenvalue. We found it. And so if you actually look at this matrix, negative 1, negative 3, 5, 7, 2 is one of the eigenvalues, and 1, negative 1 is one of the eigenvectors associated to that eigenvalue. Okay, and then we do the same thing for the other eigenvector that we were given, which let's say the other eigenvector is, let's make it funky. Let's say the other eigenvector is, where'd you go? Sorry, I lost my spot. That's not the other eigenvector I wanted. Did I not find the other eigenvector because I was lazy? Oh, there it is right there. So let's do the same thing. And so again, if you have questions, let me know. But let's do the same thing for the vector, which is an eigenvector. Let's say we're given the vector 3, negative 5 e to the kt. So again, we want to figure out what k is so that this is a solution to this equation. So meaning we need to find x prime. Okay, the derivative of this is 3 negative 5 times k e to the kt. And this is going to be negative 1, negative 3, 5, 7 times 3 negative 5 e to the kt. You point out this is your x, this is your x prime. Okay, so let's multiply it out. Well, actually, let's divide both sides by e to the kt, which is not 0. Then we're left with 3k negative 5k equals negative 3 plus 15 is 12. And I bet my life that this is going to be negative 20. Because k has to be 4 for that to be 12. Assuming I've done this right. Let me check before I bet my life. Negative 3 plus 15, and then 15 minus 35 is negative 20. So k has to equal 4, which would have been the eigenvalue we would have found, and then found this eigenvector associated to it. And then, so here's what we have. We have the solution. So the solution, right, here's one of the pieces. Here's the other piece. So we add them together. So our somewhat final solution, sorry, I'm going to erase that, k equal to 4. Our solution is that x of t equals this piece plus that piece. So it's going to be 1 negative 1 e to the kt, where k was 2, plus 3 negative 5 e to the 4t. Now we're missing one thing. Well, two things really. We're missing the, oh, no, that's fine. we're missing the constants C1 and C2, or in this problem, they say to use A and B. So this would really be A times this plus B times this. And the reason that still works is because, right, if you take the derivative of this, you still get the same thing back. So we would say here that, and this is where the notation is terrible at. We say that x of t would be a times 1 times e to the 2t plus b times 3 times e to the 4t. And y of t would be a times negative 1 times e to the 2t plus b times negative 5 times e to the 4t. And just like in the previous example, this example, both of the eigenvalues are positive, meaning everything is shooting away from the origin.